Drilling fluid, or drilling mud as many people call it, is a vital element of the rotary drilling process. The term drilling fluid includes air, gas, water, and mud. Mud refers to the liquid that contains solids in water or oil. The mud is made up with clay and other additives that give it desirable properties. Often, water is the base of drilling mud. Water makes up the liquid part, or phase, of a water-based mud. Crew members put clay and special additives into the water to make a mud with the properties needed to do its job well. For example, clays give it thickness, or viscosity. The water in the mud may be fresh water, seawater, or concentrated brine, salt water. The one used depends on its availability and whether it gives the mud the needed properties to drill the hole efficiently. At times, downhole drilling conditions require the crew to add oil to the mud. Or, in some cases, crew members use oil instead of water as the base of the mud. This is called oil-based mud. Oil-based mud has many advantages. It can stabilize the formation and reduce downhole drilling problems. However, it is harder for the crew to work with because it can create slippery conditions, and environmental precautions must be used. From an environmental standpoint, mud with oil is more difficult to handle because the oil clings to the drill cuttings. The oil must be cleaned off the cuttings before they are disposed of. Sometimes drilling fluid is dry air or natural gas. Here, dry air is coming out of the rig's buoy line, carrying very fine drilled cuttings. Air drilling uses large air compressors instead of mud pumps. Drilling with air or gas can prevent formation damage and can overcome severe lost circulation problems. And it allows the bit to drill very fast. Downhole conditions have to be just right for air or gas to be usable. For example, the bit cannot drill through formations containing large amounts of water. The water mixes with the cuttings in the air or gas and clogs up the hole. If small amounts of water are present in the formations being drilled, special equipment can inject a foaming agent into the airstream. The foam helps separate the cuttings and remove water from the hole. In some cases, the rig operator may use aerated mud, which, like foam drilling, helps prevent clogging of the wellbore. Aerated drilling uses both mud and air, pumped into the standpipe at the same time. When circulated down the drill string and up the hole, drilling mud serves many functions. For example, mud cleans the hole, cools and lubricates the bit and the drill string, lifts cuttings to the surface, carries information about the formations being drilled, stabilizes the wellbore, controls formation pressure, and suspends cuttings when pumping stops. One function of mud is to clean the hole. A clean hole allows the bit to drill into uncut formation rock. Here's an example of what can happen when cuttings are not removed off bottom. Mud jets out of the bit and moves cuttings away from the bottom of the hole. The mud then carries the cuttings up the annulus and to the surface for disposal. Heat is encountered downhole. Deep formations can be very hot, and friction from rotating drilling components generates a lot of heat. High temperatures increase drill string and bit wear. Drilling fluid helps to reduce the temperature in the drill string downhole while drilling. In addition, drilling fluid provides lubrication to the drill string and bit that also helps prevent wear. Mud stabilizes the hole, keeps it from caving in. As mud moves up the hole, it usually flows by permeable formations. Permeable formations are those that allow fluid to flow. When the mud is next to a permeable formation, pressure forces the liquid part of the mud, the filtrate, into tiny openings or pore spaces in the formation. This leaves behind a thin sheath of solid particles, known as mud cake. These solids plaster the side of the hole, much like the plaster on the wall of a building. The wall cake helps keep the hole from caving in. The column of mud in the well creates pressure downhole, called hydrostatic pressure. The hydrostatic pressure of the mud column offsets formation pressure. Mud is the first line of defense in well control. As long as the hole is full of mud that is the right weight, the well cannot kick and perhaps blow out. A kick is the entry of formation fluids into the well bore. The kick forces drilling mud out of the hole. If crew members fail to control a kick, a blowout can occur. A blowout is the uncontrolled flow of drilling mud and formation fluids out of the hole. Mud is also used to obtain information about formations downhole. Mud loggers, by examining cuttings at the surface, can gather important information about the formation being drilled and the conditions downhole. In water or oil-based drilling mud, crew members usually add a clay called bentonite or a similar mineral. Bentonite swells in water. Therefore, it thickens the mud, gives it viscosity to help clean the cuttings from the hole and provide other desirable properties. Barite is a heavy mineral. The crew adds barite to mud to make it heavy or dense. Barite is over 4 times heavier than water. Dense mud exerts more pressure than light mud. Weighted mud controls formation pressure. This is called primary well control. The control of many mud properties depends on its pH. The pH of a mud is a measure of its acidity or alkalinity. The pH scale runs from 0 to 14. If the mud is neutral, neither acidic nor alkaline, it has a pH of 7. Mud with a pH below 7 is acidic. A pH above 7 shows that the mud is alkaline. Most drilling muds require a high pH, at least 9 or higher. Because mud needs to have a high pH, another common mud additive is caustic soda or sodium hydroxide. Caustic soda is often called caustic. Crew members add caustic soda to the mud to control pH. Caustic soda increases the pH value. It makes the mud more alkaline. In general, caustics are the most dangerous chemicals that you will handle on the rig. High-strength solutions can seriously burn your skin. Be very careful when handling it to avoid injury. Wear the proper personal protective equipment. Also, remember to always add caustic soda to water. Never add water to caustic soda. If you do, the caustic soda will boil up, splatter, and cover you with a burning chemical. When drilling stops, say to let the crew make a connection, add a joint of drill pipe to the string, the driller normally stops pumping mud. When pumping stops, the mud stops moving. At rest, mud gels. That is, it becomes a semi-solid like gelatin. Gelled mud suspends the cuttings. Gelling keeps the cuttings from falling downhole and piling up around the bit. The ability of a gel to keep the cutting suspended is measured by its gel strength. When the driller starts the pump and resumes mud circulation, the mud's gel strength reduces, which allows the drilling fluid to flow easier. We have just covered a few key points about mud additives and the properties that mud should have to allow successful drilling. On the rig, it is important for crew members to constantly monitor and maintain these properties. An important member of the drilling team is the mud engineer. The mud engineer runs tests on the drilling fluid. The mud engineer's job is to monitor and maintain the mud's properties to the specifications of the well operator. He may also recommend changes to improve drilling, such as adding more caustic soda to increase the mud's pH. In this section, we will learn about tools that are used to monitor mud properties. The density, or weight per unit volume of the drilling mud, determines how much hydrostatic pressure the mud column exerts on the formation. It is therefore important to know the mud's density at all times. To determine mud density, the mud engineer or helper uses a mud balance. The person